Welcome back. We've been working with a lot of vectors over the last week or two while studying motion in one dimension. But now we would like to expand that and start looking at motion in two dimensions. So to do that, we're going to need vectors that point in two dimensions. So to do this, we're going to have a vector like this. So we have a displacement vector here of a car, and this car is driving at an angle that is 30 degrees north of east, and the car has traveled 2 kilometers in that direction. So, so this is what we need for a vector, right? We need the magnitude and we need the direction, so we have that. But if we want to find the components, the parts of this, we're going to have to be able to do a little bit of trigonometry to solve these problems. If you haven't done trig in a while, we are going to review this a bit. But to make things simple, what's going to happen is, we've spent a good bit of time learning how to think about motion in one direction, and so the good news is we're going to be doing exactly the same thing. What we're going to do is we're going to break our vectors into the x component and the y component, and then once we've done that, we can treat the x component as a one-dimensional problem, and we can treat the y component as a one-dimensional problem. Okay, so let's look at a velocity vector. So we would like to break this vector, this velocity vector, into an x and y components. So how fast is it moving in the x direction, and how fast is it moving in the y direction? So we can also describe this vector using an angle and magnitude. So all right, there's our x and y components. And then we also can define it with the magnitude of the velocity and the angle theta. So kind of like the car we just looked at, that was traveled, 2 kilometers, 30 degrees north of east. So here it's a velocity, so we're traveling at some velocity. That is some angle north of east. So notice that we've made a right triangle. So here is our 90-degree angle, and so this is our angle theta. So our adjacent angle, our adjacent length is v sub x, the x component of the velocity, and the opposite is the y component of the velocity. So that means that the cosine of theta is equal to the x component of the velocity divided by the magnitude of the velocity, and if we want to find the x component of the velocity, we take the magnitude of the velocity and we multiply it by cosine theta. We also notice that the y component of the velocity, we can find this too, because the sine of theta, so the sine of this angle theta, is equal to the y component of the velocity, the opposite, divided by the magnitude of the velocity. And so yes, we can just rearrange that. So the y component of the velocity is the magnitude of the velocity multiplied by the sine of the angle theta. So we're going to want to be able to use this angle from the x-axis as our standard angle, and so as long as we're good about doing that, then the x component is always going to be the cosine, and the y component is always going to be the sine. So yeah, I guess we should do a quick refresher on trigonometry. There are a few things that we know when we're talking about a right triangle. So one right triangle has one right angle. So there we go. There's our 90-degree angle. And so then there's certain labels on this. So the hypotenuse is the longest side of the right triangle, and this is the one that is on the opposite side of the right triangle. The hypotenuse squared, the length of this hypotenuse squared, is equal to the opposite squared plus the adjacent squared. So basically, the two other sides of the triangle squared is equal to the square of the hypotenuse. So if you know two of the lengths, then you can always find the third length using this relationship, which is called the Pythagorean theorem. The other way we can find the lengths of the sides is by using the trig functions. So we can use them because there's a relationship between the trig functions and the length of the triangle. So when we are given a second angle of the triangle, so our angle theta here, so we have two sides. So the side that is attached to the angle theta, we call that the adjacent side, and the side that is opposite the angle theta, that we call the opposite side. So remember, the longest side is going to be the hypotenuse, so this one's third side, so not the adjacent or the opposite. So this relationship is that, first of all, the sine of theta is equal to the length of the opposite side divided by the hypotenuse. So that means if we know the angle, then we know the relationship between those two lengths. So if we know the cosine theta is equal to the adjacent length divided by the hypotenuse, and then the tangent of theta is equal to the opposite side divided by the length of the adjacent side. So you probably learned this as a SOHCAHTOA, I guess. Also, when you use the trig functions in your calculator, you're going to want to use them in degree mode. So calculators can treat angles in radians or degrees. So for the moment here, we're going to be giving angles in degrees, so you want your calculators to be set for degrees. So there should be a mode button that allows you to change that. So yeah, that always causes a good bit of issues. Okay, so let's look at an example. So in this case, we have an object that is traveling at 20 meters per second at an angle that is 25 degrees above the x-axis. So we want to find the x and y components. All right, to find the x component of the velocity, all right, let me draw the angle here. So we want to find the x and y components. So to find the angle, all we have to do is multiply the magnitude, so 20 meters per second times cosine of 25 degrees to find the x component, and we do the math on that. We find that the x component is 18.1 meters per second. If we want to know the y component of the velocity, then you multiply the 20 meters per second, so the magnitude of the velocity, times sine of 25 degrees, and that gives you 8.45 meters per second, right? So for the x component, we want to use cosine. For the y component, we want to use the sine. So what does this mean? This means that the velocity at which the object is traveling to the right is 18.1 meters per second. So if you were standing there and you didn't have very good depth perception, it would appear that the object was moving 18.1 meters per second to the right. If you were over here, so if you're standing on this side, then it would appear that the object was moving 8.45 meters per second up. It means that if this object moved this way for 1 second, so it would move 18.1 meters to the right, and it would move 8.45 meters up. And if it kept this velocity for 10 seconds, then it would travel 181 meters to the right, and it would travel 84.5 meters up. So if you know these velocities, you multiply by time to get the displacement. So yeah, so there's some different notation used to describe these vectors. So a lot of the time you'll be given angle magnitude, so 20 meters per second at 25 degrees above the x-axis. We can also describe this vector using component notation. So we can say that the velocity is 18.1 meters per second for the x component and 8.45 meters per second for the y component. This is often written down where you are multiplying the number by a unit vector. So unit vector is a vector that has a value of 1 and points along one axis. So the x vector is multiplied by 18.1 and the y vector is multiplied by 8.45, and that gives us the y component of the vector. So this notation can drive people crazy because mathematicians usually use x hat and y hat or something like that for your x and y unit vectors, but we use x and y for a whole bunch of things in physics. So in general, we use I and j. So I corresponds to the unit vector along the x-axis, and j corresponds to the y vector. So all this is really saying is that it's 18.1i and 8.45j. It means that the velocity here is 18.1 meters per second in the x direction and 8.45 meters per second in the y direction. Okay, so you have a few problems to do. The main question that I think will cause issues here is, actually it's not this one, it's this one. So notice that the angle that you are given is from the negative x-axis here, so it's not the before we've been giving you this angle theta from the positive x-axis. So I guess I should point out, if you notice that if this angle is between 90 and 180 degrees, so where x is, in this case x is going to be negative and y is going to be positive. So that's the main trick on these, is figuring out the signs on the vectors is often what causes issues. But in any case, the thing I want to warn you about now is what happens if we give you this angle from the negative x-axis. Well, the way to do this is that if we rotate this thing, that rotation all the way around is 180 degrees. This is 180. And then now we rotate back by theta, so then we subtract theta. There we go, there's the theta. So the point is, now we have, if we do that, then we have our new value, I guess I'll call it theta 2, there we go. So it's theta 2, and so that's what you would want to use to find your x and y components of the velocity. So yeah, so if this angle theta, this angle was 10 degrees, then the angle from the x-axis, the positive x-axis, to the vector would be 180 minus 10, so it would be 170 degrees. Okay, so you have some questions to do, and then next we're going to look at vector addition. Good luck.